Module 3. Unit 5. Linear Programming Models, Graphical and Computer Methods. Linear programming, LP, is a mathematical method used for optimizing resources, widely applied in various fields such as business, economics, engineering, and logistics. It involves maximizing or minimizing a linear objective function subject to a set of linear constraints. The basic properties of linear programming include the linearity of the objective function and constraints, the presence of decision variables, and the feasible region defined by the constraints. The objective function represents the goal of the LP problem, such as maximizing profit or minimizing cost. Decision variables are the unknowns to be determined, and the constraints are the limitations or requirements that must be satisfied. The feasible region is the set of all possible solutions that satisfy the constraints, and it is usually a convex polyhedron. Formulating an LP problem involves defining the decision variables, constructing the objective function, and setting up the constraints. For example, consider a company that produces two products, A and B. Let X1 and X2 represent the number of units of products A and B, respectively. Suppose the company wants to maximize its profit, which is $5 per unit of product A and $8 per unit of product B. The objective function can be written as maximize Z equals 5x1 plus 8x2. The company has limited resources, such as labor and materials, which translate into constraints. For instance, if producing a unit of product A requires 2 hours of labor, and a unit of product B requires 3 hours, and the total labor available is 100 hours, we have the constraint. 2x1 plus 3x2 is less than or equal to 100. Similarly, if the material constraint is given by 3x1 plus 2x2 is less than or equal to 90, the complete LP formulation includes the objective function and all constraints. Maximize Z equals 5x1 plus 8x2. Subject to 2x1 plus 3x2 is less than or equal to 100. 3x1 plus 2x2 is less than or equal to 90. x1 is greater than or equal to 0, and x2 is greater than or equal to 0. Solving an LP problem graphically involves plotting the constraints on a graph, identifying the feasible region, and finding the optimal solution at one of the corner points, vertices, of this region. For example, the constraints form a polygon on the graph, and the feasible region is the area where all constraints overlap. By evaluating the objective function at each corner point, the optimal solution can be determined. Changing the right-hand side of a non-redundant constraint would cause a change in the feasible region. The isoprofit line method is another graphical technique used to find the optimal solution. This method involves drawing lines of equal profit, isoprofit lines, parallel to the objective function and moving them outward from the origin until they reach the last point within the feasible region. The optimal solution is at the point where the isoprofit line touches the feasible region. In linear programming, slack refers to the unused portion of a resource in a constraint. If a constraint has 20 units of slack, it means that 20 units of the resource are unused in the optimal solution. The dual price or shadow price represents the increase in the objective function value per unit increase in the right-hand side of a binding constraint. Since a constraint with slack is not binding, it does not restrict the solution, its dual price is 0. Therefore, if there are 20 units of slack, the dual price for that constraint is 0, indicating no impact on the objective function. Sensitivity analysis examines how changes in the coefficients of the objective function or the right-hand side values of the constraints affect the optimal solution. This analysis helps determine the robustness of the solution and identify critical constraints or variables. For example, if the profit per unit of product A increases from $5 to $6, sensitivity analysis can determine if the current solution remains optimal or if a new solution is required. If in solving a linear program no feasible solution exists, a constraint may need to be removed or relaxed. In linear programming, alternate optimal solutions occur when there is more than one optimal solution that yields the same value for the objective function. This happens when the objective function line is parallel to a constraint boundary within the feasible region. If a program is unbounded, the problem has not been formulated correctly and a constraint was inadvertently omitted. Linear programming problems can also be solved using computer software, such as Excel, which provides tools like Solver to handle larger and more complex problems. Using Excel for LP involves setting up the objective function, decision variables, and constraints in a spreadsheet, and then using Solver to find the optimal solution. This approach is particularly useful for problems with more than two variables where graphical methods are impractical. The difference between minimization and maximization problems lies in the objective function. In a minimization problem, the goal is to find the minimum value of the objective function, such as minimizing costs or resource usage. In a maximization problem, the goal is to find the maximum value, such as maximizing profit or output. The formulation and solution methods for both types of problems are similar, but the interpretation of the objective function differs. The role of sensitivity analysis in LP is crucial for understanding how changes in the model parameters affect the optimal solution. Sensitivity analysis helps decision makers identify which constraints or variables are critical to the solution and how much flexibility they have in changing the model parameters without altering the optimal solution. Units: Linear Programming Applications. Linear programming, LP applications, are crucial in various industries for optimizing resource allocation and making informed decisions. In marketing, LP can optimize the allocation of advertising budgets across different media channels to achieve maximum reach or sales. For example, a company might need to decide how to allocate its advertising budget among TV, radio, and online ads to maximize customer reach while staying within a budget. By setting up an LP model with the objective function to maximize reach and constraints, representing the budget and available advertising slots, the company can determine the optimal mix of advertising channels. In production scheduling, LP helps optimize the use of resources such as labor, materials, and machinery to meet production targets while minimizing costs. Consider a factory that produces multiple products, each requiring different amounts of resources. By formulating an LP model with the objective function to minimize production costs and constraints, representing the availability of resources and production capacities, the factory can determine the optimal production schedule that meets demand and minimizes costs. For employee scheduling, LP can allocate shifts and tasks to employees to maximize productivity and minimize labor costs. For instance, a retail store might use LP to create an employee schedule that ensures all shifts are covered while minimizing the total number of hours worked. By setting up an LP model with the objective function to minimize labor costs and constraints representing employee availability and labor regulations, the store can create an optimal schedule. In finance, LP is applied to portfolio selection problems, where the goal is to allocate investments among different assets to maximize returns or minimize risk. An investor might use LP to determine the optimal mix of stocks, bonds, and other assets that maximize the expected return while staying within a specified risk tolerance. The LP model would include an objective function to maximize returns and constraints representing the investor's risk tolerance and investment limits. Mixtures and blending problems involve determining the optimal mix of ingredients to produce a product that meets quality standards at the lowest cost. For example, a food manufacturer might use LP to determine the optimal blend of ingredients for a product, considering constraints like nutritional content, taste, and cost. By setting up an LP model with the objective function to minimize costs and constraints representing the quality standards, the manufacturer can determine the optimal mix of ingredients. Revenue management uses LP to optimize pricing and inventory decisions to maximize revenue. An airline might use LP to determine the optimal pricing strategy for different flights to maximize total revenue while considering factors like demand, competition, and capacity constraints. The LP model would include an objective function to maximize revenue and constraints representing capacity and demand. Formulating and solving LP problems in these applications involves several steps. 1. Define the decision variables. Identify the variables that represent the decisions to be made. For instance, in a marketing problem, the decision variables could be the amount of budget allocated to each advertising channel. 2. Construct the objective function. Formulate the objective function that needs to be maximized or minimized. In a production scheduling problem, the objective function could be to minimize production costs. 3. Set up the constraints. Define the constraints that represent the limitations or requirements that must be satisfied. In an employee scheduling problem, the constraints could include employee availability and labor regulations. 4. Solve the LP model. Use graphical methods or computer software like Excel to solve the LP model and find the optimal solution.